Hello everyone, my name is Esmahan. This program is about people from geological science. Today my guest is Philip Kasrovich. He's the manager of lab. So we'll talk about application of different techniques such as SEM, XRD, and XRF for mineral and elemental composition of rock and core samples. Welcome, Philip.
Thanks for having me.
It's honor for me to have you here. Thank you for coming to this interview. So let's begin our conversation with your background. Could you tell me about your background, education?
Sure. So I have a Bachelor's of Science in Geology from the University of Texas at Arlington. I did some research while I was there on detrital zircon geochronology. From there, I went to Colorado School of Mines and I earned my Master's of Science looking at the critical mineralogy of an Archean volcanogenic massive sulfide deposit, VMS deposit, specifically focusing on tellurium and telluride minerals. And through that, I used a variety of different methods, including SEM-based automated mineralogy, electron microprobe, that sort of thing. And then from there, I started my PhD here at Mines, doing very similar projects, looking at the critical mineral deportment of various different mineral deposits and deposit types, and also extending how we can use sort of advanced analytical techniques to get better geological data.
Oh, interesting. So you are working here, aren't you?
Yes.
Yeah. Okay.
Yeah, so I'm currently running the Minerals and Materials Characterization Facility here at the School of Mines. So we have a couple different instruments. We have this automated mineralogy system, which is a TESSCAN TEMA. Next door, we have a TESSCAN MIRA field emission scanning electron microscope. And then down the hall, we have some other instrumentation.
Fantastic. So, Philip, as our topic is about application of these techniques for mineral and elemental composition of rock samples, could you tell me about your research area?
My research is primarily focused around mineral deposits, and even more specifically, critical minerals that occur in these mineral deposits. So critical minerals being sort of these, they're all mostly elements, with the exception of like barite and fluorspar, but they're elements that we need for high-tech applications, whether that's green energy, defense applications, semiconductor research, that sort of thing. And these are also elements that are subjected to fragile supply chains. So as we all saw during COVID, everything it got difficult to get, and so these metals are no different. And so there's been a big push internationally for governments to sort of establish their own more robust supply chains for these critical minerals. There's some significant knowledge gaps in terms of how and why they occur in mineral deposits, and whether they occur in quantities which are maybe conventionally considered economic. I don't really touch on the economic side of things, but I focus on finding them, understanding why they got there, and how they occur in those deposits. And then the bigger thing for me is that I get to connect that to fundamental geological processes, right? Something had to happen to cause these enrichments or a relative depletion of certain elements. And so while there is a very tangible world need for these commodities, it's also pushing the science forward, which I really enjoy.
Amazing. So, Philip, you mentioned about tellurium-bearing minerals.
Yes.
I read your dissertation thesis about tellurium mineral characterization in Quebec.
Yep.
This is in Canada.
Yep.
So, could you tell me about it more? Why is that mineral important?
Yeah. So tellurium is used in a variety of different applications. Sort of the long-standing application of tellurium has been as a semiconductor or as sort of a technology metal. So it's been used in Xerox machines or photocopy machines, in metallurgy. So alloying copper with tellurium changes its metallurgical properties and its machining properties. So those are more the traditional uses for tellurium, but recently there have been some major advances in cadmium telluride thin film solar cell technology. So this is a pretty low cost solar or photovoltaic panel technology, which allows for essentially low-cost, high-efficiency panels. There are a lot of other competing technologies, so it'll be interesting to see how that shakes out. But that's caused a lot of kind of recent interest in tellurium as a commodity.
Okay, interesting. So what kind of instruments, techniques did you use to characterize tellurium-bearing minerals?
Yeah, so tellurides or other tellurium-bearing minerals, so like tellurium sulfides, things like that, they tend to occur in very small grains, at least in the vast majority of occurrences. They tend to be very, very small. And so traditional petrographic techniques like reflected and transmitted light microscopy are not going to be effective in really characterizing the abundance of these grains. You can certainly see them in some cases, but it's very difficult to quantify the occurrence. And so I used a big chunk of my research is based off of automated mineralogy data generated on this instrument, the TESSCAN team.
I see.
Yeah, so it's scanning electron microscope based automated mineralogy. So there are other automated mineralogy platforms, MicroProbe, XRF, but this one's SEM based, which I think is the most common.
Okay, interesting. So I have been working as a head of petroleum geochemistry in Kazakhstan for last 10 years, and that company has a petrophysical lab where SEM and XRD analysis are performed depending on the request of the customer. So I'm always interested to know the differences. So it is right time to ask this question.
Totally.
So could you tell me what is the differences between, say, working principles? Let's overall differences between SEM and XRD or XRF.
Sure. Yeah, so I'll split it up a little bit. So with SEM, for what I do, there are essentially two major applications for SEM. One of them is imaging and point analyses. So that would be the instrument next door, the Mira. And then the other would be to generate some sort of quantitative analysis over an entire sample, very similar to like a bulk measurement with XRF or XRD, and that would be automated mineralogy. So I'll split the SEM camp in that way. So with SEM imaging, we're able to get to a much higher resolution. A field emission source is really crucial for getting super high resolution images, and I can image telluride grains on the hundreds of nanometers scale with some reliability. Whereas this instrument is fantastic for what it does, but it's not designed to do extremely high resolution imaging. It's a tungsten filament SEM, and those typically have a little more limitations when it comes to the resolving power. So actually, you'll see that a lot of SEM users are moving towards field emission sources because they're just getting more and more popular and more available and for better prices. So that was a very useful tool for imaging very small grains, for doing point analyses on very small grains, to essentially verify what I was seeing by automated mineralogy. But again, if I were to go over an entire sample and point count in SEM at 50 micron field of view, it would take me ages to do so, right? So with automated mineralogy, we're able to automate that process and go through and collect data relatively rapidly over a large area. So that allows me to quantify the mineralogy of an entire sample. And I retain things like the textural characteristics, the grain size distribution, things that might tell me more about differences between my samples that would be difficult to quantify statistically through just imaging or microscopy. And then when you move into like XRD, XRF, those are much more commonly referred to, I guess, in what I do as like a bulk analysis, right? Similar to like whole rock geochemistry, in that you're taking away a lot of the textural context of the sample in order to get a representative view of sort of a homogenized material. So XRD is very useful for identifying clay phases, various silicates, which are compositionally really similar. Because with SEM-based methods, we're only defining phases based on chemistry. We don't know anything about their structure. We don't know anything about polymorphs or things like that, which, or at least we don't get information on those from SEM.
Okay.
So if it's not something that's chemically defined, it can be very difficult to pick apart using SEM. Or if you have very fine-grained interwoven magnesium silicates, for example, that can be a really challenging prospect.
So anyway, we should talk about these instruments separately. Let's begin with SEM.
Sure.
So could you tell me the working principles and what detectors are there?
Electrons. Those electrons are then funneled through a series of electromagnetic lenses and coils and things like that down to a beam. In this case, you're currently 600 nanometers across in our beam size. So that's a fairly broad beam, but we're doing a fairly broad analysis. We don't need super tight beam for that. But next door, we can go down to something like 5 or 6 nanometers pretty reliably. That beam is then focused to a point, like I said, in the chamber. So this actually opens and we can insert samples, and that beam then interacts with the sample, hits the surface of the sample. So there's a couple different physical interactions that we take advantage of with SEM imaging and analysis. The first of them is the backscattered electrons. So these are electrons that actually penetrate the surface of the sample and then interact with the matter of the sample and are scattered back to the detector. And so those tell us something about the chemistry and the material of or the chemistry and physical properties of the material that we're looking at. Another effect that we take advantage of is secondary electrons. So these are the electrons that hit the surface of the sample and are immediately reflected back. Those tell us about the topography of the sample, very much like photons hitting any surface and bouncing back towards your eyes. That's how secondary electrons work. Or at least similarly. And then when we have an electron beam interacting with the atoms of a sample, electrons are very, very small. So if you imagine your Bohr model of an atom, you have a nucleus, and then you have essentially rings of electron orbitals. Those incoming electrons from a beam can come down, displace one of those inner shell electrons, and cause instability in the atom. An outer shell electron will have to drop in to fill that void, and in that drop, it releases energy in the form of an X-ray. Those X-rays have characteristic energy levels, and so we can detect those using these detectors. These are called EDS detectors or EDX detectors, which stands for Energy Dispersive X-ray Spectroscopy. So by detecting those characteristic energies, we can then look at something like this over here, and we generate a spectra on the right here. And at each of these points along the screen, along the x-axis, this corresponds with a specific energy level, and that energy corresponds to certain elements. Through that, we can look at the proportions of elements and determine what the mineral is.
You mentioned about backscattered electron detector, so it gives magnified images of the sample. Yeah.
So the backscatter detector, the SEM in general generates a large amount of magnification because we get a very small spot size, so we can resolve very small features. The backscatter detector is better for understanding the chemistry of the sample. So the intensity of the backscatter is a direct function of the mean atomic number of the material that you're looking at. So if you think about it, think like a sponge is very soft, right? Versus like steel, which is extremely hard. If you were to throw something at the sponge and throw something at the steel, you're going to get a different level of rebound.
Yeah.
It's less about the hardness and more about the density, I suppose. So something like a lead mineral is going to be extremely bright. Gold is going to be extremely bright, whereas quartz is going to be significantly less bright because it's composed of light elements.
Okay, so it depends on the density. So denser elements.
Mean atomic numbers.
Okay, good. Yeah. Okay. Next question. Let's talk about XRD.
Mm-hmm.
So, in XRD, amorphous and crystalline substances can be differentiated. How can they be differentiated in XRD?
Well, in XRD, for in amorphous phase, you would expect to see sort of a broad round peak, whereas for crystalline phases, you should have relatively sharp peaks along your diffractogram. That's what I know as far as the differentiating factor. Yeah.
Okay. Next question. Does the XRD have any disadvantages
Yeah, sure. So XRD
in comparison with SEM, XRF, for example?
totally. So with XRD, for the most part, a lot of the data that you get is either major, minor, or trace when it comes to the actual abundance of a certain mineral phase. It's very difficult to accurately quantify the modal abundance of your mineralogy. You can do the Rietveld refinement, which can get you a lot closer. Something like this technique, closer to an actual mineralogical sort of breakdown of your sample, or something like a whole rock estimate of your sample for geochemistry. But I think in general, XRD is only sensitive to several weight percent of mineral abundance. Whereas with SEM-based automated mineralogy, we can very easily go into tenths and hundredths of a percent abundance for different mineral phases if they're of interest, right? And a lot of that is a factor of your data reduction process. And
Next question. Let's talk about EDS detector. So how does it look? It gives spectra of the elements. So some elements elude or come out earlier than other elements. So why is that?
yeah, so with an EDS detector, you're looking at those characteristic X-ray energies produced by the electron beam interacting with the atoms of the sample. And so when you have that happening, you have a few different things that you're relying on. You're relying on sort of statistics, right? You want or probability, I guess is a better way to put it. The probability that an incoming electron strikes an electron in the material, displaces it, and you have that outer shell electron dropping down and releasing an X-ray. And so that probability can be enhanced by having a greater concentration of a particular element, right? And so you get your spectra growing at a different rate based on the concentration of elements in your sample. So, for example, if you're looking at galena, your lead and sulfur peaks, which overlap, but they would grow at a much higher rate than any silver, which may or may not be in the galena, just as an example, right? And so those peaks represent the characteristic energies, X-ray energies for each element. So when you look at a periodic table that has sort of the X-ray energies for each element, you'll see that there are a few different options. So I have one on the wall, just looking at titanium, for example. You have an emission at 4.5 keV and at 0.452 keV. And so those numbers represent different transitions from different electron shells. So you have like a K alpha peak and a K beta peak, things like that. And so that represents electrons from the K shell making a specific transition and releasing a specific energy for that. So when you look at any given spectra, you may have multiple different peaks for one element, and that just represents the different transitions. And so those peaks have characteristic patterns to them because of sort of, like I said, that probability that one transition happens over another. And so we have to also have incoming electrons of sufficient energy to overcome this excitation energy. So using titanium as an example again, with that 4.5 keV X-ray, if we want to excite that, we have to at least give it 4.5 keV beam intensity or beam voltage. So right now we run it at 25 keV.
Okay.
So we can excite pretty much the entire periodic table. But that also means that you have some different interactions that occur with a powerful beam.
Okay. Interesting. So we talked about different detectors and different techniques. So in SEM, secondary detector, backscattered electron detector. So which often penetrates or analyzes the sample deeper?
Mhm. Yeah, so backscatter is going to give you the greatest information depth, and that depends on how you have the beam set up. But it can be anywhere from half a micron or hundreds of nanometers to microns plural. And that just depends on how you have your beam set up. Something like a secondary electron detector or an in-beam secondary electron detector is going to give you just a very thin look at the surface. There are some techniques which combine the two methods so that you can get really nice topography while also getting some indication of the chemistry. So certain instruments, the one next door can do that, where we can essentially combine two different SE signals to produce it's sort of a combination of chemistry and topography.
Okay, interesting. So, Philip, last question. A scattered electron detector gives magnified images of the sample. Yeah. So it also here we can do this elemental mapping.
Yes. Yeah.
That elemental mapping. So how does it get such information? Is it based on the identification of elements? It's based on, say, mass spectra or spectra from EDS?
Yeah.
Okay.
So there's a few ways that we can use backscatter intensity to do mapping, but when it comes to chemical mapping, that's purely based off EDS. So we can actually take a secondary electron image and overlay EDS chemistry on top of that. So those interactions with the matter of your sample, those I guess they're physical interactions in the physics sense, right? Those physical interactions are always occurring. So you always have backscattered electrons, and you always have X-rays being scattered. It's just that's how electron beams interact with matter. And so it doesn't really matter what detector we're using at the time. If we want to add EDS, we just have to have an EDS detector. If we want to overlay VSE, we can actually mix those channels and do things like that. But chemistry or element maps with EDS are really interesting and they can produce some very cool data, but they're also important to be careful with because that spectra, like I showed you, those peaks can be fairly broad depending on how you have your detectors set up and depending on your detectors. So the broader those peaks are, the more they're going to take over the positions of peaks which might be next to them. So let's say, like lead and sulfur, for example, where peaks are right on top of each other. And then you have bismuth, which is right next to lead. And so if your lead peak is fairly broad, it may start to look like you have bismuth in your sample. And so the way that these element maps are generated, in some cases, the software, if you say, oh, give me an element map for bismuth, it will basically put a marker on the bismuth peak position and look at the magnitude of the peak along that point. So if that magnitude is the lead peak extending out into here, suddenly you have trace amounts of bismuth.
Okay, so
But it's not real, right?
It might be misidentification.
So it's very important to be intentional and very important to understand sort of the physics behind how these methods work before over-interpreting some data.
Interesting. And also, we use, say, XRD SEM results in oil and gas industry to determine hard parameters. Porosity, permeability, for example, is elite or is high, it leads to low permeability. The second is thermal maturity, for example. Elite symmetric ratio also gives information about this. And formation damage. And also information, this elemental and mineral composition gives information about environmental condition, for example. Yeah? This. So that's why we attach much importance to this analysis in oil and gas industry. Thank you, Philip, for this interview. It was very useful and interesting. And I attended your course on XRF, and I am going to attend your course lectures on SEM and XRD analysis. So good luck with the PhD dissertation. Thank you for coming.
Thank you.